Okay, well, let's talk about the homework. Hopefully it's easy to follow what to do. Try to be as detailed as I can be. So for number one, they're asking you to evaluate the limit and to approach it from a numerical perspective as well as a graphical perspective. Whether you did exactly three values on each side, I didn't care. I mean, if you put 3.999, 4.01, that works for me. Of course, there's an algebraic way of thinking about it. You could factor the bottom and cross off the common factor, and you should get 1 over x plus 1, I think. And if you put in 4, you should get 1/5. But, I want you to explore numerically and graphically what's happening, and you do get 1/5. And there's a hole there, obviously, at x equals 4. For part B, we'll talk about algebraic, how to approach that as well. See, again, if you plug in 3, you're going to have an issue, right? You're going to have 0 over 0. Um, so that's an issue. So instead, what we do is we could plug in numbers close to 3 or look at the graph on Desmos, and there's a hole. So you can always just mouse over to 3 on Desmos. That's probably the best. If you use Desmos, that's totally cool. 100% that's totally fine. Actually, I prefer you do that over the TI-4 calculator because it's a little more challenging to find the holes. You just mouse over, right? It's easier to visualize. So I would just do that for part B. Part C, that actually should be 1. The one way you could think about it, sine x is approximately the same thing. Not exactly, but if you plug in values very close to like 0.00001, sine of that is pretty 0.00001. So they're really close together. So that should be 1. And actually, the graph does look like this. We haven't talked about it yet. We'll talk about more in this class. It kind of does something like this here. That's how the graph looks. By the way, if I change this up, text approaching infinity, given how the graph looks, and the fact that you're doing infinity, if you think numerically, right? What's the range for sine? From what to what? No range, not domain. Domain's by all real. You're thinking of -1 to 1, right? You're thinking of the unit circle. But the bottom keeps getting larger, right? So ultimately, what's the value of expression heading towards? 0 exactly. So that would have been 0, by the way. We'll talk about that too. Part D, kind of common we see sometimes. That's just 1. Um, yeah, just 1. G, that's gonna be 1 as well. 2, A through F, those are all the answers there. That was from a graph, I think, if I'm not mistaken. Yeah. Yeah. So if you're approaching -2 from the right side, it's going up forever. -2 in general, we just don't know. By the way, if you said D and E for part A, I would accept that. But if you're being a little more explicit, yeah, sure, it's positive infinity, -2 from the right side. But -2 in general is a two-side limit because the left and right sides are going totally different places. That doesn't work. 0 also does not exist. 2, of course, is looks like 1/2. Hard to tell. 4 is positive infinity or does not exist. You can say that as well. But f of 4, of course, is 2. Yeah. Yeah, infinity or does not exist for part E. Both work for me. Either are fine. Okay. And then lastly, for 3A, we kind of saw this already in the notes. Um, x minus 2. Now, it's just like absolute of x over x. It's just the same thing, but one little change is a transformation, of course. What is the transformation here? Wait, right to, correct. Thank you, Laura. So it looks like that. But still, it's going to be 1 or -1, and of course, the limit does not exist. The left-hand limit is -1. The right-hand limit is +1. They don't line up, right? That's a problem. So we won't exist. It won't exist regardless, even if it's shipped. Um, you can also write as a piecewise function, by the way. Um, yeah, you can see here. This is true when x is less than 2. This is true when well, if you're doing this, that's just x minus 2 over x minus 2, which of course becomes 1. That's true when x is greater than 2. So that's what's happening there. Okay, well, cool. All's good. All right. Okay. No questions? All right, let's keep moving the notes. So our plan is to start at the top of page 6 and go to the and page 7's very short. Page 8's blank. Page 9 and 10 are also pretty short. And today's gonna be more algebraic. We're gonna talk more about algebraic ways to find limits. And there's a variety of algebraic techniques we'll take into consideration. Before we do that, though, we should talk about root x. That's kind of an interesting case here. You guys should know root x looks like this. Now, I did say earlier on the previous page, we said this on Monday? Yeah, Monday. Sometimes you just plug in. If you just plug in, what do you get? 2. There you go. I mean, if you want to look at it, sure, go ahead. Just 2 anyway, right? However, however, this one does not exist. That's kind of a funny situation. But why?
Because it's not approaching from the left.
Good. Look at that. Wow. All right. You should teach this class. That's because there's no left-hand limit or root x not defined for x less than 0. Because right now it's written as a two-side limit. Right? That's written as a two-side limit. So instead, what should we say? The limit is what? If you want to be okay at 0. What would you, a slight wrinkle you have to add to this? Yeah, you gotta do that. Correct, right? The RHL is okay. The RHL is okay. But you don't have left-hand limit. So just keep that in mind. Just something, just one little nuance about limits, about root x that sometimes people sometimes don't think about. But we got to go with the hardcore definition, right, of a limit. You got to have two sides. If it's not defined, forget about it. You only have a one side. Hi, Miles. All right. Okay. So anyhow, let's move on. Okay, now the fun begins. This is the part of limits I love. And this is where I could really push you guys and challenge you guys. And we're gonna see some really crazy ones. So let's get crazy. All right. So if you're asked to find the limit of something like this, right? Always try direct substitution, see what happens. See what happens. Oh, geez, I don't want that. You get 4 minus 4 over 2 minus 2, which of course is 0 over 0. The problem is that 0 is called indeterminate. So we can't determine. And one little nuance I think we should talk about. Why do we call that indeterminate? And also, let's compare 0 over 0 versus 1 over 0. So 1 over 0 we call undefined. 0 over 0, sorry, I'm trying to sneak that in there. We call indeterminate. It's kind of a subtle thing, but there's actually a difference. Does anyone know why one is called one way and the other is called the other way? Does anyone have an idea or no? I could explain it if you don't, but because
Is it like no answer versus like not a clear answer?
yes, 0 over 0 is not clear. Indeterminate means you can't determine. Okay. Or to be determined. Like, for example, if you're going to have like a soccer game or a playoff game, it's to be determined. You don't know yet, right? It's not clear. But here, undefined means there's no definition, not possible. Let's think about it from a very simple arithmetic perspective. I mean, you know this, right? 10 divided by 2 is 5, of course, right? You wouldn't be here otherwise. Okay, we don't let you into the school. Okay, 10 equals 5 times 2, right? Duh, obviously, right? Or what if you have 0 over 2? Of course it equals 0, right? Because doesn't 0 equal 0 times 2? If you move the 2 over to the other side, right? That makes sense. So anything times 0 is always 0. Okay. So when you get 0 over 0, it could actually equal any number. It could be anything you want. And you probably haven't realized that, but it can. Because what if I move that 0 to the other side? Does 0 equal any number times 0? Yeah, of course it does. That's why it's indeterminate. It's not clear. We don't know what 0, 0 is. It's an unknown. Doesn't mean there's not an answer. We got to do a little digging, which we are going to in a moment. We're going to do some algebra to dig a little bit. Just you can't determine it by substitutions. We have to do something else, which we'll do in part B. 1/0 is a problem though, because if you set 1/0 equal to a number, can one equal a number times 0?
No.
No, that's not possible. Hence, it's not defined. So if you ever were unclear about that, sometimes we misconstrue these or we conflate these things. So anyhow, just want to make sure you guys are clear on that because I feel responsible to talk about that. So instead, what should we do? Yeah. Now, this is one part you're guys are not going to like this. It's going to be a little upset at me. You got to write that limit notation until you finally plug it in. You can't get lazy. If you really want to feel Ms. York's wrath, you don't do this, you will feel her wrath. I'm a pretty nice guy. I'm pretty calm, pretty chill. So I'll just kind of just with a smile take out points. And you're like, please, please, like, no, sorry. It's okay. Just do it next time. You got to write the limit notation because you haven't valued the limit yet, right? Some people get lazy and don't write it, or they just kind of just half-ass it. You really have to write until you're ready to substitute. So these go away. So now what am I taking the limit of? Yeah. But Ms. York is a very nice person. I didn't even put her on the bus. She's very, but she can sometimes be a little tough. Equals 4. Yeah. But by the time I'm ready to plug the 2 in, then you could drop the limit notation. But you can't get lazy. Even on the AP exam, they are very that particular. They're very, very strict. So I need to get you guys in habit of writing it.
Hey, but once I have the expression I'm going to use, I don't need to write it anyway.
Correct. Right. Once you have the expression you want, then you're ready to substitute, then you're good. Like if you wrote over here, if you wrote the limit as x approaches 2 of 2 plus 2, I wouldn't hold that against you. It's just redundant. It's not necessary. Because there's no more x anymore. But once you've plug in for x, you're done. Okay. So hopefully we're okay on the formality of it. And I don't take up that many points. Like I kind of just do like a global kind of thing, like kind of look at your test. And if you missed it once, I'll forgive you. If you miss like 4 or 5 times, I'll take up a point. Like, don't worry about it. If you miss it, if you never do that, I might take up 2 points. So I just do this more of a global thing than anything else. Okay. This was where the real fun begins. Thoughts on what should I do here? Yes, conjugate. Yes. There we go. Well, said so. Well, what does that mean, though? What does that mean? How about that? Can you tell me what that means?
I don't know how to do this one, but if it was like x plus one, then you do x minus one.
Yeah, it's similar. So you want to switch a sign in the middle. So I'm going to rewrite this. Because what's going to happen, you multiply the conjugate, the radical goes away. Right now, the radical is a problem. See, if I plug in right now, what's the problem? You get 1, you get 0 over 0. So it's no good to substitute. We have to get creative. That's what I like to call getting creative. How do I get creative? The conjugate. And that's a big tell is if you have a radical. That's a huge tell. Root x plus 1 plus 1 root x plus 1 plus 1. So you have to FOIL. Now, if you FOIL, what happens? What do we get? Plus 1 minus 1. The radicals do go away. And the bottom, don't distribute it because you're going to be substituting anyway and canceling out anyway. Actually, if you distribute, you make it worse. Because what is the issue right now with the original expression, the x in the bottom? Because if I plug in 0, I get 0. That's a problem right now. Would it be nice if it went away? 100%. So don't distribute it because you want it to go away. And I'm being lazy, so I got to write this also. Don't be lazy. Okay. Now, the top becomes x. The bottom is x. And I do have this urge to be lazy, but I'm not going to be lazy. I'm going to fight that urge. Okay. The x's go away, right? Then I get 1. Now at this point, can we substitute 0 for x? Now you can ignore the limit notation. And if you do that, what do you end up getting? No, no. If you plug in 0 for x after you cross off the x's, 1/2, right? You get 1/2. Yeah, what minus? You didn't get 1/2?
No,
Oh, yeah, okay, cool. All right, good, good. All right. So we have some practice on this in the homework. Lucas, go ahead.
you had a problem that was like one of those.
So what's going to happen with that when there are sometimes we do see that, that's going to be infinity or negative infinity, depending on whether x is approaching 0 from the left or right, or depending on what the bottom is doing. That's going to be infinite in nature. Like if you have 1 over x, for example, right? But it depends on what side you're approaching. So sometimes that can happen, but usually for these problems, I want like a nice, neat solution. So that's the intention of these problems. But yeah, if you do get that, it would be some sort of infinity, positive or negative infinity. All right. Let's try another one here. Okay, so we have fractions. So you should find the LCD. So if I do that, I get 1/3 minus 1/3 over 0. 0 over 0, no good, right? So instead what I'm going to do is find my LCD. What is my LCD? Yes, 3 times x plus 3. Now, what I like to do, you could do a couple ways. The LCD, by the way, is, as you guys just said, 3 times x plus 3. Okay. So what I'm going to do is this. I'm going to multiply top and bottom. You could also just combine the two fractions up top. But then you have to flip the fractions afterwards. I don't know. I kind of like just to bust the fractions right away. See, what I'm doing here is I'm multiplying all this to this fraction and to this fraction. So take a close look at 1 over x plus 3 in red. Multiply to the LCD 3 parentheses x plus 3. What happens when I multiply the fraction 1 over x plus 3 to my LCD? What crosses out? So you get 3. And what if I multiply the other fraction, 1/3, to the LCD? What crosses off? So you get that. And the bottom becomes this. Again, the x is an issue right now on the bottom. Now, we can clean it up. If you clean it up, you should get this, right? The limit of what over what? Negative x. Cool with that? Now, what goes away? And that becomes what? Negative 1. So you have negative 1 over 3 times 3 parentheses x plus 3. Now I could substitute. Negative 1 over 3 times 3, negative 1/9. So you get a nice, neat answer. Oh, so right here, I cleaned up the top. So I should negative x minus 3.
Okay.
The 3's cancel. They should cancel. That's the whole intention. We want it to cancel. So we're being incredibly intentional here, right? When we do this. So factoring, conjugates, LCDs, these are all in your toolkit, right? These are things. So when we made you guys, to be honest, like we made you do all this stuff last year or in middle school, things like that, it's really to have it for calculus. We want these skills because we're going to have to eventually do derivatives. We will do derivatives later this semester, and derivatives involve limits. We're going to have to do limits like this over and over again. Of course, the techniques for derivatives are more efficient than because you keep doing it. To keep doing this algebra is going to get kind of painful. So we'll have more efficient techniques down the road. But for now, we need to get in a habit of understanding the algebra of the limits, right? What we're trying to do here. We're okay with this? So we can move on. All right. All right, let's move forward. Okay, for a piecewise function, um, well, part A is easy. What's x approaching here? Oh, you're good. Yeah, yeah, come back to class. Come on, man. Get back in there. All right. Okay. Sorry. I have my little Rich Dealy moment there. He would like actually yell at people like that. If you ever heard him yell, he's like big crazy. Anyway, he's a good guy. Anyway, which one am I going to go with? The first or second? Second, yeah, I got a little distracted. I'm going to go with the second because obviously it satisfies that condition. So when you do the limit as x approaches 3, you're doing of what expression? Because the condition. Yeah. The condition, what we're approaching only satisfies the second condition, not the first condition. Because piecewise functions are all conditional. You got to choose the expression that the condition satisfies. It's not satisfying the first. It's satisfying the second. Top bottom. Okay, we're good. Okay, cool. Everyone's good. So now you can plug it in. You get 6 minus 3 squared. 6 minus 9, you get -3. Now, part B, however, is a slight issue. Because remember, this is all about approach. So we need the LHL and the RHL. We need both. So, I'm going to take the limit. And the limit is x approaches 1 from the right. Okay. If I approach 1 from the left side, so remember x is less than 1. It's close to 1, but it's really close, but it's still less. Like 0.9999999. Which one am I going to go with, the top or bottom expression? So I'm going to do -2 times 1 plus 2. And of course, the other one is going to be the bottom one, right? 2 times 1. Because 0 does not equal 1, or the LHL does not equal the RHL. You can see why I abbreviate because I'd go crazy if I had to write that out, left hand, right hand limit. Then what do we say? Does not exist.
So you only worry if the answer is 0 when it's 0 over 0 and not like 0.
Well, correct for doing algebraic stuff, but for piecewise functions, because we're approaching right, that was the previous examples. But for this specific example, for part B, x is approaching a number that's at the boundary of the piecewise function, right? Because what's a boundary here? 1, right? Because that's when we have to make a decision. At 1, are we going to go at the top or bottom? We have to make that decision, right? That's where weird things could happen because you have two different expressions. They may link up, they may not. And do these link up? They do not. There's a hole there. In fact, actually, we call it jump discontinuity. If you look at graphically what's happening, hold on, Marie. If you look what's happening, it's going to be something kind of like this here. Actually, it's 0. Hold on, it's a negative slope. Yeah, it's like this, and that's going down, I think. Yeah. That's what's happened graphically. These don't link up. Hence, the limit would not exist. We see that visually. But from a numerical or algebraic perspective, we have to plug into the right expression. Hey, to the left hand, the right hand. Do they link up? No, they don't. Those are different outputs. That's a problem. So we say it does not exist. So we're cool with that too? Yeah, right, good. Hmm?
It's different for, like, you have to look at those five and like not for
A.
A.
Because we already know where we are at 3. At x equals 3, I'm already on this curve. Because x is larger than or equal to 1. So by the time I've already passed this boundary, I'm like way over here now. So I can just look at it. If I approach 3 from the left to right side, it's a nice, smooth, continuous curve. It's all about like smoothness or continuity, really. Because when you're in this region, when you're at x approaching 3, so you're getting closer to 3 from either side, 2.999, 3.01, you're over here now. You're not dealing with this nonsense.
And then when it's,
But for B, we are dealing with this nonsense. You have to look at it like, well, they don't link up, so they don't exist.
and you have to look at it from both sides. One is like the starting point.
Yeah, the reason we look at, but you always look at both sides. You always do for all limits. But some are just so simple, like part A, because we'll just look at. I mean, sure, I could look at both sides, but that's just kind of redundant. Just see what happens. Like if I plug in 3 and negative 3, doesn't matter. But here, because of this situation, because there's a possibility they could link or not link, we have to look at because one is to separate these two. That's how you tell by the boundary. That's where weird stuff happens because you're defined the piecewise function in that manner. Oh my God, yeah.
On the curve, you just plug in whatever.
Plug it in. Yeah,
And if it's
100%.
not fine there, you just
Correct.
figure out a way to get it to not be undefined.
Correct. Right. Yeah. Okay, from the homework. Okay, let's move on to part 2. I'm not gonna do all part 2. I'm only gonna do a couple pages, and then I think that's good for today. Yeah, we're doing great on. Oh shit, I forgot to update the time. Sorry, I know we're done by 10:25. We've still got plenty of time. All right. So we saw this in the homework. Sine x over x is 1. If you do tan x over x, it's also 1 as well. Hope I don't break my computer because Desmos sometimes slows things down. If I do graph y equals tan x over x, yeah, it looks like this. And if I mouse over, you see there's a hole there. So it's undefined. So yeah, it's the same thing, you know. You get 1. Now, what if I decide to kind of mix things up a little bit? It says sine x over x is sine 5x over 5x, or tan 11x or 11x. I'm just going to tell you right now what happens. What if I do 11x? Whoa, that's crazy. Okay. If I do that, oh, that's interesting. Okay. Still the same thing. Or if I do like sine 5x over 5x, still the same thing. So whenever you change the coefficient of x in the sine function or tan function and do the same change of the coefficient for the denominator for x, you get the same thing. It'll still be 1. So this happens, you just get 1. The starbursts, this is actually the previous teacher who taught this, or I co-taught with many years ago. She liked the starburst mainly because it's important. That's just something to memorize, something to know. Just accept it as fact. This is what happens. I think there might be a more formal proof. I don't want to get into that. Plus, I need to look it up. I forgot what the formal proof is. But yeah, that's what happens. Sine kx over kx, tan kx over kx. Um, Another way you could think about it too. By the way, actually, just to help you guys think about it a little bit, you could actually, I am going to give you a little formal proof because it just kind of hit me. What if we let a equal 5x? Then what does x equal? It sure, right? Yeah, 100%. So if I were to rewrite this, right, I'm doing the limit as a over 5 approaches 0 of sine A over A. Well, think about it. If a over 5 is approaching 0. Isn't A approaching 0? How's A over 5 going to get to 0 anyway? Right? How would any fraction get to 0? The numerator has to get to 0. What's my numerator? A. So A over 5 approaching 0 is the same as A approaching 0. So if I take the limit of this as the input variable approaches 0, the input variable is totally arbitrary. I can do whatever I want for my variable. I can do any letter I want. What's that going to be? Still 1 anyway. It doesn't matter, right? It doesn't matter. It's still going to be 1. So if you do a substitution for 5x or 11x or anything, that proves that kx over kx, the sine kx over kx or the tan kx over kx, doesn't matter. It's 1. However, it gets a little bit different for these here. I'm just going to tell you right now the answer is 9. Now, why? Why is that 9? Well, I could graph it, but I'm going to do the same exact thing. I'm going to let A equal 9x. So x equals A over 9. So I'm taking the limit. Does that make sense so far? Yeah. Now what happens is I could flip over the bottom fraction. And by the way, the same thing saying A is approaching 0. If A over 9 is approaching 0, A is approaching 0. So now you got 9 over A times sine A. Or if I use my limit properties, we talked about this the other day, I could break it off like this. It's actually a great application of limit properties. Okay, before I move any forward, you guys with me? We're cool with what I'm doing? Yeah, right. So I just did this, right? Replace x with A over 9, right? Did a little algebraic manipulation, did all the stuff. And I could break it off like this. Should be pretty comfortable for your fractions. You have 9 over 8, say sine over 8. It's like 3/4 times 5 is 3 times 5/4, so same thing, right? And if that's a constant, of course, what's that limit going to be? Just 9. And we already know what this is. That's a known entity. What's that going to be? 1. There we go. 9 times 1 is 9. Now, I'm not going to ask you to kind of show me all this work because this is going to be part of a bigger problem, as you can see for some of these other problems we're doing. What I will ask that you memorize. You could totally just go straight to this. It's just going to equal K. It's just going to equal K. So we can assume that. All right. Let's look at part B. We're almost down here. You guys should have plenty of time working homework. Um, Thoughts on part B? Good. I like that. That's a good idea. Yeah, right. And also just to check, 0 plus 0 over 0, 0, 0, that's no good, right? I don't like it. So let's factor out the x. I think it's a fantastic idea. And those will cross off. So you get, so now here's when I'm going to use the limit property again. You're allowed to do this. You get 3 sine x over x plus what's the limit? What are each of these individual limits? 3 plus 1, which of course is 4. There you go.
It's a program kind of separated like this, you have to, right, if you change the original.
You do. Yes, you do. Because you're using the property. Here we go.
Project X equals 0, like, isn't the denominator 0 for the first one?
No, but we saw this already. Sine x over x. We established that. What's the limit of? Right. This is established limits, and you multiply by 3. We already established that.
Keep the pieces together, add them, build it.
What do you mean by that?
That's splitting it into two.
You want to split it 2 because you have to show what each of the individual limits are. I mean, you could, when you get very good at this, you could just see it, but you have to prove it, right? So you have to do 3 sine x over x and x over x. X over x is just 1. We know that. And 3 sine x over x is, I mean, we already know. I mean, if I want to be a little more long-winded about it, I could have added an extra step in the middle. It's the limit of x approaches 0, 3 times limit of x approaches 0 of sine x over x. I didn't feel like doing that because I think you guys could see sine x over x is 1. We know that already. So that's what you get 4. Okay, does that make sense? Those are the ones that are get a little trick. Ooh, all right. There's some good ones here. All right. You know what? I'm going to let you guys try this. You guys try C and D. You guys can handle it now. All right, I'm gonna do it, and I'll freeze my screen, and then we'll talk. You guys can handle this. So you're gonna have to get a little creative here. No, not at all. Nope. No identities. Nope. Yeah, identities actually have very little role in AP calculus. I think I heard someone say it right. Try, I think you got it. Don't say it out loud, though. I think I heard you. What was it? Sorry?
You asking for C?
Yeah,
19 thirds?
I got 2. I heard someone. I thought you said 2. There. That's what I did. I factored x in the bottom. You got 11x plus 3. Of course.
No.
Course you can. Okay, so this is it's fraction root 2, guys. So just remember, yeah, no, that's okay. That's okay. This is where this is good for me to know. If you have A over B times C, that's the same thing as A over B times 1 over C. You totally could do that, right? You're decomposing the fractions. So that's A okay. That's when you have to get a little creative here.
E, where did E come from?
Just came out, just there.
Wait, E's being multiplied.
Correct. These are all being multiplied. Just kind of give you an idea of what to do for part D. Part C, we're okay. We're okay, part C. We're already moving to part D. Yeah, here you have sine 3x, e7, tan x all being multiplied. 5x squared, without realizing it, that can be broken apart as three factors, 5x and x. And I'm being super deliberate of putting x below sine and tangent. Why am I going to do that? Because I have a rule for it. Let's use that rule. So if I think about it, what do I get now? I get 3 times 1 times that junk, whatever that is. That's a constant. There you go. Oh, yeah, or CLG, I know. I just tried to symbol because I didn't want to. Yeah, that's funny. I just realized that. Thank you, Emma. I appreciate that. Okay. All right. We're good on part D. Awesome. We're almost done. Good. Okay. Example 3. Um, Trying to think here. Um,
Multiply by the.
yeah, the conjugate, I know, but it's a fourth root. That's why I'm just I'm a little just give me a sec. Let me think this one through here. If I do that. I do. Yeah, let's do the conjugate. Okay.
No, but the,
Okay.
no.
I'm kind of taking a leap of faith just so you know, because I don't fully remember the solution for this one. We'll see what happens. Okay. If I do this, definitely the radicals go way up top, right? I wind up getting 1 plus h raised to the 2/4 power, which is just square root, of course, right? Okay. The limit as h approaches 0. Okay, do you guys see how I got 1 plus h raised to the 2/4 power? Because you're multiplying a fourth root to itself, so you have two of them. But really, you can just reduce the exponent, make it 1/2, which I know is square root anyway, right? So what do you guys think I should do next?
Yeah.
Do it again, yeah. Yeah, I'm pretty sure I have to do it again. Again, kind of taking a leap of faith here that this will work. I think it will work. See the limit. Oh, you're right. It's plus. My apologies. Yes, thank you for catching that. So 1 plus h minus 1 over h, fourth root. Now, of course, these cancel. So you have h over h. I know it's getting very cumbersome to keep writing this one. That's your SAT word for the day. But more cancel, right? What else cancels? Yeah. And I kind of want you to write it again because I don't want you to cross off too much in one of the steps because it gets kind of confusing. Now I could plug in 0 for h, and I get this. Final answer, 1/4. Both are okay with that. Okay. It's a perfect time to end for today. So yeah, I'm glad I kind of thought this through really well. So your homework's going to be homework 4, which is stated here. There's a few problems you have to already put up in Schoology as well. So you're going to be doing these analytically. You got some th fun stuff to do here. You also have more on the next page. And then also you have number 5, A through F. Yeah, I already said that. Oh, you also have some of these other ones, part C of number 3 and number 4. We have that as well.
No. Like, yeah. Like to 7.
Once you no longer have undefined on the bottom, no longer have 0 on the bottom. Once you cancel out a single variable, because a lot of times these limits are x approaching 0, or x approaching like a number that causes a factor to be 0. Once you cancel something else, that's the pattern because you're going to start seeing this over and over again. Yeah, and then we also have uh 1 through 3 here on the next page, on page 3. And then just more graphical stuff, reviewable other stuff. So, all right. So the homework's already there. It's not due till, well, it's actually due tomorrow. So I see you guys tomorrow. So you get a head start if you like. Yeah, it's homework can be a little more intense. And then we do have a quiz tomorrow also on graphing a polynomial function, rational function. So we go. I already did. Yeah, should be there. Hold on. Yeah, if you click here and click on homework quizzes, it's there. Yeah, or if you click on this, it's there as well. Yeah, 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 it's there. I'm trying to think of a lesson for tomorrow. Yeah, tomorrow's lesson is pretty short. Looks like just a couple pages. I'm going short, so you guys can watch the Niners on the weekend. So, yeah, should be another good game. Not until February 8th.